Exponential Manual. Objective: I will be able to simplify expressions containing exponents. Essential question: how could I use properties given to me to simplify expressions? The focus teak is 11B. Take a few minutes, decorate the front of your book. This is the table of contents. Use this to figure out where you want to go when you're looking back at your notes. Page 1. Evaluating roots. So we have three functions here. F of x equals the cube root of x minus 1. G of x equals the square root of 2x plus 3. And h of x equals x to 3/2 power minus the square root of x plus 5. Using these functions, we're going to evaluate the roots at these given x values. F of 1 will have the cube root of parentheses 1, close parentheses, minus. And this is what you would type into the calculator under calculate. Once you type it in, you should get 0. Okay, f of negative 7. Do the same thing, except for now instead of a 1 inside parentheses, we put negative 7. If you type that into the calculator, you should get negative 2. And now we're going to replace the x with a parentheses 20. Notice it has the approximation symbol instead. That means it's going to be irrational, and you're going to type in just how you had the first two, but you're going to get a decimal output. We get 2.6684. The next one we have g of 8. So we're going to use the g function to find this. So instead of x, we put in parentheses 8. And if you put that into the calculator, you get 7. Next one, we replace x with parentheses 12.5. When you plug that into the calculator, you'll get 8. Now let's plug in for x 50. G of 50. You should get 13. Okay, now let's look at the last function, h of x. So for each x, we're going to plug in the number that it has here to evaluate these functions. So for the first one, after we substitute each x as 1, we get 5. H of 0 is also 5. And the last one, h of 3, we'll plug in 3 for each x. And we put that in the calculator, we get 8.4641. We put this in the calculator. Page 2. Evaluating powers. So on this page 1, we're evaluating roots. On this page, we're evaluating the powers, expressions that have an exponent. So go ahead and write these out and see if you can figure them out. Pause the video, start it again when you're ready to check these. For the first function, you should get 23, 1, and 9. Now try the g function. Here's what you should get for the next three. 3, 1.414, and 1.732. Okay, try the h function now. And here's what you should get on those functions. On page 3, we're going to be doing evaluate exponents. So this is another calculator exercise. Pause the video, see if you can do these. Unpause it and see what you get, if they're correct. Here's what you should get approximately for each of these. Page 4, evaluating logarithms. Now we're not going to formally go over logs in this class, but you will need them for Algebra 2. When you're simplifying square roots, you want to pull out perfect squares. Those perfect squares include -1, 4, 9, 25, and 49. If you're able to pull out those perfect squares, you should be able to simplify almost any square root they give you that has just a number. So with 24, can we pull out -1? There's no negative. How about 4? We can divide by 4. 24 divided by 4 is 6. Now, 6 does not have a perfect square you can divide by. So that's just your remainder, your leftovers. The square root of 4 equals 2. So our simplified radical would be 2 square root of 6. Let's look at the next one, the square root of 108. It's not negative, so we can't pull out that. 4. We could divide this by 4. 108 divided by 4 is 27. We can't take out any more 4s, so we're done with that. How about 9? Yes, we could divide by 9. 27 divided by 9 is 3. There's nothing else we could take out of 3, so that's our leftovers. Square root of 4 is 2, and the square root of 9 is 3. So our answer would be 2 times 3 times the square root of 3, also known as 6 square roots of 3. For the next two, we have variables as well. So what you want to do is separate these two into two different expressions and then put the answers together later. So we know that the square root of 24 was 2 square root of 6. We have a negative here though, so we're also going to take out a negative 1, which the square root of negative 1 is I. So we have 2i square roots of 6. Now with the square root of a variable, we have x to the 5th. We're going to rewrite this as a power. So we have x to the 5 over 2. Every square root will have a fraction with a 2 in the denominator. Now 5 over 2, 2 goes to the 5 2 times with a remainder of 1. So that means the 2 goes on the outside exponent and the 1 goes on the inside. So it looks like x to the second power square root of x to the first power. So this 2 goes on the outside, this 1 goes on the inside. So we're going to put these two expressions together. So we have 2x squared I square root of 6x. So for the last one on this page, we have the square roots of 108x to the 10th power. We'll separate the number and the variable. We have 108, and then we'll have square root of x to the 10th power. So we already did the square root of 108 over here. So we just write that again. We could also pull out the square root of 9 first, and then the square root of 4. And you'll get the same answer. I always like to put them in order from least to greatest, so I don't miss any. But you can also do from greatest to least on this list. You'll get the same thing. Now with the square root of x to the 10th, it's going to be x to 10 over 2 power. Well, 10 over 2 is 5, so you have x to the 5th. So we'll just put that, and that's our simplified radical. Page 6 is simplifying cube roots. So instead of square roots, now we're going to simplify cube roots. The perfect cubes we want to try to take out are these numbers that are right at the top. We'll try to take out negative 1, 8, 27, and 343. Let's look at the first one, the cube root of negative 8. Has a negative, so we could take out a negative 1. Take out the cube root of negative 1. So now we have the cube root of 8. We can also take out an 8. We just get 1 right here. The cube root of negative 1 is 1, and the cube root of 8 is 2. Negative 1 times 2 is negative 2. So your simplified radical is negative 2. Let's look at the next one. The cube root of 54. There's no negative, so let's go to the next one. Can we take out 8? No. We can take out 27. 54 divided by 27 is 2. So we have the cube root of 2. There's nothing else we could take out of that. So that's our leftovers. So our simplified radical would be 3 cube root of 2. How about the cube root of 32? No negatives. We could take out 8. Cube root of 8. So 32 divided by 8 is 4. Now unlike square roots, we can't simplify that anymore. So we just have 2 cube root of 4. Cube root of 8x to the 8th power. So just like on the previous page, we're going to separate the number and the variable. So we have cube root of 8, which we already know is just 2. And we have the cube root of x to the 8th, which we're going to change into an exponent, x to the 8 over 3. The denominator will always be whatever number this is. If there's no number there, we assume it's a 2. 3 goes into 8 2 times without going over. And 2 times 3 is 6. 8 minus 6 is 2. So our remainder is also 2. So we have x to the second power on the outside. And on the inside we have x to the second power as well. It's the outside. The remainder goes to the inside. So our simplified radical is 2x squared cube root of x squared. That's it. Now we're getting to what 11b is all about. Simplified exponents. We have product of powers. Product of powers is adding exponents. Quotient of powers is subtracting exponents. Power of a power is multiplying exponents. Rational exponent, which we're just doing, is dividing exponents. Negative exponent, you flip the fraction. There's no change in the signs here, except for with the exponent. So we have negative n at the top, and when you flip it, the n becomes positive. It works the same if this is a negative in the denominator. You just flip it. Flip it over the bar. Page 8. Product of powers. Go ahead and write down these expressions, and we will cover these in class. Here's an example. 3 to the 7th power times 3 to the 2nd power is the same thing as 3 to the 7 plus 2 power, 3 to the 9th power. See if you could do these before we go over them in class. Page 9, quotient of powers. We're subtracting the exponents. Try these, write them down. We'll go over these ones in class. Here's an example. We have 7 to the 15th power divided by 7 to the 3rd power. That's the same thing as 7 to the 15 minus 3. That's 7 to the 12th power. Notice that we have to have the same base in order to do this. So for example, if this was a 7 and this was like an 8 or something, we couldn't do that. It would already be simple. Page 10. Power of a power. We'll multiply the exponents. Write these down. See if you can do these before we cover them in class. Here's an example. We have 4 to the 2nd power to the 5th power. That's the same thing as 4 to 2 times 5 power, which is 4 to the 10th power. We can also distribute here. So if we have like 2 different bases inside of here, we'll just have the first base to this outside power times the second base to the outside power. An example for that would be 3x to the 4th power. That's the same thing as 3 to the 4th power times x to the 4th power. That's 81x to the 4th power. A common mistake on here is only distributing it to the x and not to the number, the coefficient. Don't forget to do that. Page 11, rational exponent, dividing exponents. In the radical expression above, n is the index, a is the base or the radicand, and m is the power or the exponent. And the math symbol, like that looks like this, indicating the taking of the roots, is the radical. The index tells us what root is being taken. Here's some examples. The square root of x is x to the 1/2 power. The cube root of w to the 5th power is w to the 5/3 power. Try these and then we'll go over them together in class. Page 12, negative exponent. That's when you flip the fraction. Here's some examples. We have x to negative 1. It's 1 over x to the first power. It's just 1 over x. Here's another one. 3 over 7 to negative halves. So we flip that fraction. 7 over 3. And we change the sign to a positive. Distribute that 2 into each base. 7 squared over 3 squared. And they could have the answer like this, or they could also have 49 over 9. Try these, and then we'll go over them together in class. Page 13, other exponent properties. We have the identity. We have the identity exponent property. A is just equal to a to the first power. Here's some examples. We have the zero exponent property. Anything to the 0 power is 1, unless it's 0 to the 0th or something. But any other number to the 0 power is 1. 20 to the 0 power is 1. X to the 0 power is 1. 3,600 to the 0 power is 1. Simplify these. To simplify these i's, it wants us to look back at page 3. So if we turn back to page 3, we have our i's right here. I to 0, 1, 2, and 3. And then it cycles over again. So we're going to divide the power by 4, and whatever the remainder is, that's what the answer is. So let's go ahead and do that. So I have 42 divided by 4. 4 goes to the 4 one time. 4 goes to the 2 0 times. And we have a remainder of 2. The remainder is all we care about for these. So that means we have I to the second power. Now let's do 61. 4 goes to the 6 one time. 4 goes to the 21 5 times. Our remainder is 1. So that means we have I to the first power here. And then the last one, I to the fourth power. 4 divided by 4 is just 1 with no remainder. So that means the remainder is 0. So we have I to the 0th power. Remember, anything to the 0th power is 1. On page 14, we're going to put the properties together. So let's look at number 1. We have 4xy to the second power times 4x cubed y to the negative halves. So first, let's multiply our numbers together. 4 times 4 is 16. And let's put all the positive exponents at the top. Leave them there. And we'll flip the negative exponent to the bottom. From here, let's add the exponents of 1 and 3. X to 1 and x to the third. So we have 16 x to the fourth, y to the second power, all over y to the second power. 2 minus 2 is 0, y to the 0th power is 1. So those cancel. We're left with 16. We have 16 x to the fourth. That's it. It's our simplified expression. Number 2, m to the third times n to the second, all cubed. So take the exponent 3, and we multiply it by each of the exponents. So we have m to the ninth times n to the sixth. M and n are different bases, so that's it. Number 3, negative 2v cubed over negative v to the negative 2 power. So these two negatives right here will cancel out. It's positive. Since we have a fraction, we're going to be subtracting the exponents. So it's going to be 3 minus negative 2. 3 minus negative 2 is the same thing as 3 plus 2. That's 5. So we have 2v to the 5th power. And then the last row, this page number 4, we have x squared times x squared all over negative x to negative 2 power. Let's simplify the stuff on the inside of the parentheses first. We're going to add these exponents together because we're multiplying the bases. So we have x to the 4th over negative x to the 1st, all to negative 2 power. If we expanded this, it would look like this, and we would cancel out one of the x's. So now we have negative x to the 3rd power because there's 3 x's left to negative 2. So we have a negative exponent, so we're going to flip the fraction, and now it turns into a positive 2. Negative 1 squared is 1, and x cubed to the 2nd power is x to the 6th power. That's it. That's our simplified expression. On page 15, we're not going to go into it too much, but we're expanding and condensing log properties here. Here's the identity property, examples, and the zero log property and some examples. Your change in base formula. On page 16, we have our log product. That is the property where you're adding two logs together with the same bases, and you multiply the two numbers on the inside of the logs. Keep this for reference for later on. Same thing with page 17. We have the log quotient property. You're subtracting the logs. Here's condensing, so from 2 terms to 1 term, and expanding from 1 term to 2 terms. Page 18, we have log powers. Power rule. Basically, if we have an exponent inside here, you can move it to the outside, and vice versa. Okay, page 19. Solving roots and extraneous solutions. So remember how after you solve an equation, you want to plug the number back in to see if it's a true statement? If it does not give you a true statement, and you followed all the steps correctly, it is what you call an extraneous solution. Let's plug in these numbers for x and see if they are extraneous or they are real. Let's plug in x equals 0 first. So if 0 equals the square root of 5 times 0. Well, 0 equals 0, so that works. So that's a real number. Let's plug in the other x value, 5. Does 5 equal the square root of 5 times 5? The square root of 5 times 5 is 5. And so that works. That's also a real solution. So there's no extraneous on this first example. Let's look at the next one. We have negative 8 and 7. So if you were to solve this equation, you would get both of these answers. Let's plug them in and see if either of them are extraneous. Let's plug in negative 8 first. Negative 8 equals the square root of 56 minus negative 8, which is a plus 8. Well, we can stop right here because we can't get a negative from a radical. So that's not the same. Those are not equal. But it is a solution. But it's not real, so it is an extraneous solution. Let's look at the other one. Does 7 equal the square root of 56 minus 7? 56 minus 7 is 49. The square root of 49 is 7. That's real. Let's look at this one. X equals the square root of 12 minus x. Let's plug in the first number, -4. Is -4 equal the square root of 12 plus 4? We can stop right here because we can't have a negative equaling a square root. So those are not equal. So that means that this solution is extraneous. Let's look at 3. Does 3 equal the square root of 12 minus 3? Well, 12 minus 3 is 9. And the square root of 9 is 3. So 3 is a real solution. Let's plug in these numbers into this equation. So -2 equal the square root of 2 minus -2. No, because we can't have a negative on the outside of a square root. They can't equal each other because the square root will always be greater than or equal to 0 if it's real. So that means that -2 is an extraneous solution. Let's look at 1. Is 1 equal to the square root of 2 minus 1? Yes. So that means it's real. How about this one? If we solve for n on this one, we would get only 4. 4 is repeated twice. Let's see if it's real or extraneous. Let's plug it in. Square root of 9 minus 8, because 4 times 2 is 8. Is that equal to 4 minus 5? No, again, we have a negative on the outside here, and a negative can't equal a square root of something. So that means it's extraneous. So no solution, no real solution. Let's look at the next page. Solving roots. So to solve the root, we're going to do the opposite of a square root, which is a square. So get rid of this radical, this square root right here. We square both sides. We raise both sides to the second power. That cancels out the square and the square root. So if x equals 36. If you were to plug that back in, it would be a real solution. Let's do the same thing with this one. Raise up to the second power so we could get rid of the square root. So we get 1 equals x. If we had a cube root instead of a square root, we would raise each of these to third power. On this next one, we have square roots on both sides. We still do the same thing by raising both to second power. It gets rid of both of the roots. There's no more roots, so we just have 3x minus 21 equals x minus 3. Solve it like any other linear equation. Minus 1x minus 1x on each expression. 3x minus 1x is 2x. Carry down everything else. Add 21 to each expression. 2x equals 24. Divide each term by 2 to get x equals 12. If you were to plug that back in here, you would get a real solution. Let's look at the last one. We also square these to get rid of those square roots. To get rid of square roots, we take the square. To get rid of squares, we take the square roots. They are inverses of each other. They are opposites. Let's solve this equation. We have 3a minus 8 equals 40. Add 8 to each expression. So we have 3a equals 48. Divide each term by 3 to get a equals 16. That's it. Number 21, solving exponential equations. I'm not going to go over any additional examples here, but keep this for reference. To get rid of a base, we take the log of that base on each expression. That cancels these out. So then you're just left with whatever's in the exponents. You'd solve for x from there. 22. Solving logarithmic equations again. So this is the opposite of what page 21 was. On this one we start with exponents. On this page we start with logs. So we just do the exact opposite of what we did here. Instead of log basing both sides, we exponent the base on both sides to get rid of all those logs that you're not familiar with. And then you're just left with what's inside the parentheses on both sides. Solve for your variable, and then that's it. Now we're going to go on to a slightly different topic. It's still exponents. We're going to talk about discontinuities. We're going to talk about the different definitions of discontinuities. So remember, we did talk about discrete, and we did talk about continuous. But continuous graphs are sometimes not continuous everywhere. Like on this one, for example, is continuous everywhere except for this hole right here. A hole is a break in the function that can be filled in with a point. And on your graphs, you may or may not have a point somewhere else on the graph. These are found where the variables cancel out in the numerator and denominator. For example, if we had x over x, there would be a hole at x equals 0 because the x's cancel out. And if you set what cancel out equal to 0, that's where the hole is. The next thing is vertical asymptotes. This right here, this dashed vertical line. It's the vertical dashed line on a graph that the function never touches. To find the vertical asymptotes, you would set the denominator equal to 0 and solve for the variable. Now you would do this after finding the holes. Like so for the example, the x over x thing. You wouldn't set the denominator equal to 0 yet. You would do it after you crossed out the hole. Horizontal asymptotes. Those are the ones that you'll use the most this year. The horizontal dashed line on a graph that the function never touches. To find those, you just take the leading coefficient of the numerator and denominator, and that would be your horizontal asymptote. Oblique asymptotes. These are asymptotes that are neither vertical nor horizontal. They could be diagonal, slanted, or a curve. You won't see oblique asymptotes until pre-calculus. Let's go on to the next page, page 24. We're going to identify if each of these functions are growths or decays. Now, growth has a base that is greater than 1. Decay has a base that is less than 1. Basically, growth functions are increasing and decay functions are decreasing. If you recall from your linear notes, increasing is going from low to high, and decreasing is going from high to low. So f of x equals 2/3 to the x power. The base is 2/3. 2/3 is less than 1. That means it's decay. It's decreasing. That means that the graph would look something like that. The next one, 7 to the x power. 7 to the x power is a growth because the base is 7, and 7 is bigger than 1. This next one, it is a fraction, but the numerator is larger than the denominator, so that means that it's still a growth. It's bigger than 1. F of x equals 10 times negative 4 to the x power. Go ahead and graph this on your calculator. See the interesting picture that comes up. Do you think that picture is growth or decay? Nah, it's not either of those. It's neither growth nor decay. Graph it. You'll see what I mean. And then we have negative 8 times 0.26 to 2x power. Now, this one is a decay. Now, if you graph it, it's technically increasing, but the amount that it's increasing by is getting smaller and smaller. Page 20. Graphing exponential functions. So we have y equals 3 to the x minus 2 power plus 2. The domain is going to be all real numbers. It's going to be increasing because it is this 3 is the base is bigger than 1. So growth. And the range is going to be everything that's bigger than 2. So y is greater than 2. We get that from this 2 right here. Horizontal asymptote is y equals 2. It's that dashed line that it never touches. And behavior basically is going to go from 2 to infinity. The x-intercept, there's no x-intercept because it never crosses that horizontal asymptote. The y-intercept, if you plug in 0 for x, get y is about 1/9 plus 2. So like 19/9. Transformations, it goes right 2 and up 2. Let's make a table with x and y. Let's plug in 0, 1, 2, and 3. If you put those in the calculator, you'll get that 2.1 repeated right here. And then if you plug in 1, you get 3. 2 would be 5. And 3, you get 11. So let's go ahead and plot these points on the graph. So we have that, we'll first make our horizontal asymptote at y equals 2. And then let's plot our points. So we have 2.11 approximately. At 1 we have 3, 2, 5, and 3 we have 11. And we just sketch a graph from there. It doesn't have to be perfect. And that's it. That's our graph. Let's do the next one. We have 5 times 1/2 to the x power. Let's make a table with the x and y. Let's go ahead and use the values -2, -1, 0, and 5. So if we plug those into the calculator, or just on the paper, we get 20 for -2. For -1, when we plug that in, we get 10. 0 would be 5, and 1 would be 5/2. From here, let's go ahead and plot our points so we can get a look at the graph before we answer the questions this time. So I have -2 and 20, -1 and 10, 0 and 5, and 5 halves. That's 1/2. And then we could go ahead and draw our graph. Look kind of like this. Now the domain of this is the same as the other one, all real numbers. This was decreasing and it's a decay. Our range is y is greater than 0. How to get that? If you look at the equation, there's no number added, so we really have a plus 0 right here. In behavior, it goes from positive infinity to 0. Not to be confused with the infinity sign. This is a 2. The horizontal asymptote is y equals 0. Let's go ahead and draw that on our graph. And then the x-intercept, there is no x-intercept, so you put none. And then the y-intercept we found right here is 0, 5. And basically the y-intercept is 0, comma, this number plus whatever this is. 5 plus 0 is still 5. On page 26, we're graphing a log function. You could graph this in your calculator. Basically, it's almost the same thing as graphing an exponent function, exponential, except for everything's turned on its side. The domain and the range are flipped, and you're looking for a vertical asymptote instead of a horizontal. Go ahead and write this down, and then we'll go to page 27. You'll want to use your TI Inspire for the next page. We're doing exponential regressions. The focus tick for this was actually 9E. Now, here's the data. The data at the right shows the cooling temperatures of a freshly brewed cup of coffee after it is poured from the brewing pot into the serving cup. The brewing pot temperature is approximately 180 degrees Fahrenheit. So we have time minutes, that's X, and temperature Fahrenheit, or says Y. So on your paper, write down some notes about what I'm going to show you on the calculator. It's just like linear regression, except for we choose a different option at the end. So we'll go ahead and go to our graphing calculator. Make sure you're writing this down. You can use pictures or words. Click on the green beaker, Vernier Data Quest. Now notice there's a bunch of pages open, and when we click this, there's a number already here. Let's get rid of that. Let's clear it out. We press Control, W, no. And then start over. Press the green beaker, click the table, type in your values. We are finished with the X column. Type in the Y column's numbers. After you've typed everything in, double check to make sure everything is typed in correctly. And you don't have something highlighted like this. They're all the same size. When you're finished with that, you'll click the middle icon, the graph view, and then press Menu, 4 Analyze, 6 Curve Fit, and 6 Exponential. You click down till you get A, B, and R. And then you'll write that down on your notes. So, based on our calculations, A was approximately 171.46, and the B, the base, is 0.988. So that would be our exponential regression model to represent the data. We're going to compare and contrast the R for exponential, linear, and quadratic regressions. So let's do the same thing, except for this time for linear. So press OK, Menu, 4 Analyze, 6 Curve Fit, 1 Linear. We'll find that R value. It's -0.9695. And then we'll do quadratic regression. Press OK. Press Menu, 4 Analyze, 6 Curve Fit, 2 Quadratic. Our R squared is 0.9967. And if you were to take the square root of that determination coefficient, it would be about 0.998. If you were to take the determinant coefficients for each of these, a quadratic would clearly be the best fit. Now, why is it the best fit? It's because the coefficient is furthest from 0. The closer it is to 0, the less accurate. The further away from 0 it is, the more accurate it is with the data. The regression model is more accurate with quadratic in this case. So let's go ahead and write our quadratic equation right here on this line. So we have A, B, and C for the regression. We have y equals 0.03x squared minus 3.99x plus 180.1. Based on this new equation, what would be the initial temperature of the coffee? Initial temperature basically means when x equals 0. Well, if we plug in x for 0 for each of those, we just have plus 180.1, which is very close to that original temperature. Where does a coffee at a temperature of 106 degrees based on this equation? So we're set the equation equal to 106. So we have 106 equals 0.03x squared minus 3.99x plus 100. Now the reason for this is because if you look at the quadratic model graph, notice after it reaches its minimum point, it starts going back up. Now, unless there's an external force going for the coffee, it would not heat up again. It would continue to cool down until it reaches a plateau, which would be like an asymptote. So although the quadratic model would be more accurate between 0 and 66.5, if they were to predict anything after that time, they would want to use the exponential graph instead.